We continue to learn Chapter 6, Eigenvalues. Section 1, Eigenvalues and Eigenvectors. Part 2, Product and Sum of Eigenvalues. If p lambda is a characteristic polynomial of A, then p lambda equals the determinant of A minus lambda I. And if we write in this form, you can have this determinant of this n by n matrix. The main diagonal entries are A11 minus lambda, A22 minus lambda till ANN minus lambda. All the other entries comes from the matrix A. Okay. Expanding along the first column, we have a determinant of A minus lambda I equals A11 minus lambda times determinant of M11 plus summation I varies from 2 to n AI1 from the first column AI1 times minus 1 power I plus 1 times the determinant of MI1. So this is just the cofactor expansion of this determinant along the first column. Where MI1 doesn't contain the entries A11 minus lambda and AII minus lambda, right? Because if you're deleting this row and this column, this will deleting the AII minus lambda, this row, and also this column containing A11 minus lambda. So the degree of lambda in determinant of MI1 is smaller than n minus 1. The highest one, the largest one, can only be n minus 2. So the degree of lambda, which has degree n and n minus 1, can only obtained from the first term. So we have A11 minus lambda times determinant of M11 is the only term of P lambda that has the terms of lambda power n and lambda power n minus 1. Expanding determinant of M11 in the same manner, one can say that the term lambda power n comes from this product. A11 minus lambda times A22 minus lambda times till ANN minus lambda, and its coefficient is minus 1 power n. And if lambda 1, lambda 2 till lambda n are the eigenvalues of this matrix A, then we have P lambda equals minus 1 power n times lambda minus lambda 1, lambda minus lambda 2 times till lambda minus lambda n. And this one equals lambda 1 minus lambda times lambda 2 minus lambda times till lambda n minus lambda. Therefore, we know that lambda 1, lambda 2 till times lambda n. Okay, this multiplication equals P0 if you choose lambda equals 0. And if you choose lambda equals 0, see here, lambda equals 0 means you just compute P0 equals determinant of A. So we know the determinant of A just equals the multiplication of the eigenvalues. Similarly, also from this term A11 minus lambda, A22 minus lambda till ANN minus lambda, we can say that the coefficients of n minus 1 term, power n minus 1 term minus lambda power n minus 1 is just summation I varies from 1 to n AII. So only one bracket you choose AII, and all the other bracket you should choose minus lambda. Then you have this minus lambda power n minus 1 term. Again, from P lambda equals lambda 1 minus lambda, lambda 2 minus lambda till lambda n minus lambda, we obtain the same coefficient as this one. Summation I varies from 1 to n lambda I. So this tells us that the sum of eigenvalues is equal to the trace of A, that is summation lambda I varies from 1 to n. The summation of all the eigenvalues equals the summation of all the diagonal entries, AII. And the summation of all the diagonal entries is called the trace of this matrix A. See this example. Let A be a 2 by 2 matrix. Then determinant of A equals minus 5 plus 18, right? Minus 5 plus 18 equals 13. And the trace of this matrix A equals the summation of these diagonal entries. So it's 5 minus 1 equals 4. The characteristic polynomial of A is this 5 minus lambda, here is minus 1 minus lambda, minus 18, 1. So do the determinant of this matrix. Here we should have a determinant, okay? The determinant of this matrix equals lambda power 2 minus 4 lambda plus 13. You can get its eigenvalues. Lambda 1 equals 2 plus 3i, lambda 2 equals 2 minus 3i. And then you know that lambda 1 plus lambda 2 just equals 4, equal the trace of A. We can check the conclusion we just obtained before by mathematical analysis, okay? And also, lambda 1 times lambda 2 equals 13, which is also the determinant of A. So the determinant of A just equals the multiplication of all the eigenvalues, and the trace of this matrix equals the summation of all the eigenvalues. Now we have this theorem, 6.1.1. Let A and B be n by n square matrices. If B is similar to A, that is B equals S inverse times A times S, then the two matrices both have the same characteristic polynomial and the same eigenvalues. So here we know the similar matrices using different bases for the same linear transformation. We have the matrix representation A and B. They are similar matrices. And when similar matrices, then you can have B equals S inverse times A times S for invertible matrix S. And then we claim that they have the same characteristic polynomial, a determinant of A minus lambda I and the determinant of B minus lambda I. They are same. Because they are same, then they have the same eigenvalues. The proof we see together. Okay, if A is similar to B, then there exists a non-singular matrix S such that B equals S inverse times A times S. Let PA lambda and PB lambda be the characteristic polynomials of A and B respectively. Thus, we have PB lambda equals determinant of B minus lambda I, where B can be written as S inverse times AS minus lambda I. For this identity matrix, we can pre-multiplying by S inverse and post-multiplying by S, and this one is just identity matrix. And for this matrix, we can put S inverse in the left and put S in the right, and we write in this form. So S inverse times this matrix A minus lambda I times S. And for the determinant, for the multiplication of determinant equals the determinant of the multiplication of determinants. So it equals the determinant of S inverse times determinant of A minus lambda I times determinant of S. And we also know that for inverse matrix, determinant of S times determinant of S inverse equals 1. So this one just equals determinant of A minus lambda I. And determinant of A minus lambda I just equals the characteristic polynomial of matrix A. So it's PA lambda. So PB lambda equals PA lambda. Because they have the same characteristic polynomials, then of course their eigenvalues are the same.